Good afternoon. My name is Keith Marzullo, and I'm the Dean of the College of Information Studies. And I'd like to welcome you to our first Dean's Lecture for the year 2022. I don't know how many of you know of Olin College. If you don't, you should. It is arguably the best engineering college in the nation in terms of undergraduate education. It's truly a phenomenal place. And our speaker today is a professor at Olin College of Engineering. Indeed, she's one of the earliest faculty members. The college is in Needham, Massachusetts. Our speaker, Dr. Debbie Chachra, does research in infrastructure, materials, and undergraduate engineering education, including the design of learning experiences and investigation of student perspectives and pathways. She writes, speaks, and consults widely on these topics, and is currently writing a book on infrastructural systems for Riverhead for publication in 2023. Prior to joining Olin, she held a postdoctoral fellowship at MIT, and she earned her undergraduate and graduate degrees in engineering, physics, and material science, respectively, at the University of Toronto, which is one of the best engineering colleges in the world as well. And so with no further ado, let me turn it over to Dr. Chachra. Thank you.
Thank you for that very kind introduction. I'm coming to you today from I realize my sort of stereotypically messy professor's office in Needham, Massachusetts. It's a pleasure to be here. Thank you so much for the invitation. I'm going to jump right in, I think, which means I'm going to start by sharing my screen. So that should work. If someone could give me a thumbs up and confirm that's all good. Beautiful. As Dean Marzullo said, I'm a material scientist by training. That's what my graduate work is in. And she started off in engineering science and physics, and I care about infrastructural systems. So today, that is mostly what I'm going to be talking about. I'm going to be talking about, I said, rocks, clouds, and lightning, which is sort of the energy and the materiality and the infrastructural systems that underlie digital and infrastructural technology, digital and information technologies today. So I certainly heard this from my students, and you probably hear it from your students, but there's a sort of conception of the digital world as being weightless and immaterial and ephemeral, the idea of sort of pixels flickering on the screen. And I actually feel like that is captured, and the reality of it comes when you talk about things like the cloud, because the cloud is something that seems like it's sort of, again, weightless and immaterial and floating and transient. And of course, I realize that it's probably not sort of well appreciated that the average cloud weighs somewhere in the neighborhood of 500 tons. Clouds are actually large, heavy objects that are deeply engaged with energy. And so that's sort of what our focus is on today. So this talk is being bookended with Ursula's. I'm going to start with Ursula K. Le Guin. And I love this quote and this definition of technology that she has. So she wrote, "If technology is how a society copes with physical reality, how people get and keep and cook food, how they clothe themselves, what their power sources are, animal, human, water, wind, electricity, and other, what they build with and what they build, their medicine, and so on and on." And she wrote, "Technology is the active human interface with the material world." So one of the reasons why I love this quote is because Le Guin was talking very much about pushing back against the idea that high tech is not the only technology, that all of these systems are technology. And as someone who's particularly engaged with infrastructural systems, you can see why that resonates with me. But her line, "Technology is the active human interface with the material world," is just as true for things that we consider to be high tech, computational digital technology. It's just as true for that as it is for things like knitting and cooking. So because all technology is interacting with the material world, and this is, I said, where my materials and physics background comes in, energy is the currency of the material world, that there's nothing that happens in the world, in the material world, that does not involve energy. And so I'm going to start by talking about energy, and I'm going to start by taking us back just about 3 centuries to the first sort of economically feasible, viable steam engine, which is the Newcomen atmospheric engine. And this was devised to pump out coal mines. So it ran on coal as the fuel, and it burned to produce steam, and that the engine was then used to pump out coal mines, which allowed you to dig out more coal. And what this is, one way of thinking about, so actually, well, first of all, I should point out it was not particularly efficient, but you didn't actually have to be a particularly efficient coal-fired engine if you're in a colliery, because there's just coal around. But the thing I really want to highlight is that it meant that you could take a small amount of the coal that you mined, use it in this pump, and therefore find yourself able to pump a great deal more, or sorry, pump it out, which meant that you can mine a great deal more coal. And this is sort of the literal definition of sort of exponential growth, right? A positive feedback loop, where a small amount of coal used for the pump led you to be able to get a much larger amount of coal out. And in other words, a small amount of energy that went into the process allowed you to get a much larger amount of energy available to do other things. And that pattern has, of course, been the pattern that shaped our world for the last 200 years or so. And you can see that exponential graph, if you plot the energy usage of humanity over the course of time, you can see that it sort of rises steeply, rises because it's exponential, it rises slowly for the first 100 years, and it's been rising ever more steeply since. And you can sort of see, if you look at the legend, that the traditional biomass, the energy used with things like burning wood, has been roughly constant. And the big increase has largely been through fossil fuels, coal, oil, gas. And then you can see at the top, the rising amount of things like nuclear and hydropower. So this has been one of the things, this exponential growth in energy usage has been one of the things that's really shaped, I was going to say our society, but really all human civilization for the last 200 or so years. And there's a few sort of implications for this. So one is this increase in complexity of technology that's been made possible by both the amount of energy that's available, but also by systems of cooperation that have grown up around this. So the ability to work together to create things that are far beyond the capacity of any one human to understand, much less make. And I have, to go from the Newcomen atmospheric engine to this is a nuclear power plant. It's actually the one near where I grew up in Pickering, just on the outskirts of Toronto. But this is actually true. I mean, if wherever you're sitting, wherever you're looking at this, this is true for probably, I would say 95% of the objects that are within reach of your hand. So certainly the electronics, but even things that seem trivial, like a pen or a pencil, very little that is of our technology, of our artifacts today, can be now sort of encompassed and made by one person. That all of our technology encompasses some complexity. So that's the first step. The second thing is that this ability to reinvest fossil fuels, to reinvest this energy, allowed these systems to grow in considerable scale. And so if you look at, the Newcomen engine, and you look at a nuclear power plant, or if you look at the difference between, the Wright Flyer and a 747, right, that things can just get sort of physically larger, as well as more complex, right, because there's more energy that can be put into these systems. And the other thing that I want to highlight is that fossil fuels allowed these systems to basically grow in spatial extent, so that in geography, to sort of move farther distances now across the landscape. So three things: one, this increase in complexity; two, this increase in scale or size; and three, this increase in spatial extent. And so these together lead to what we think of, what Ursula Franklin calls the real world of technology, that we live embedded in these global networked systems. So electricity, of course, is the one that we're pretty much all familiar with. And electricity is typically handled on sort of a continent scale. So in North America, I suspect that most people listening to this certainly are, if you're in the North American grid, it's a series of interconnected grids that connect and span the continent, including both the US and Canada. This is also true, so it's true for electrons. It's also true for supply chains, so things that move atoms around. These are actually these are the new container cranes at Boston Harbor. These were put in last fall. So the rise of containerization in the middle of the last century really changed the economics of moving around physical atoms. And it changed essentially the transportation costs have dropped to a tiny fraction, effectively a negligible fraction of the cost of items. So again, this is that combination of sort of cooperation and standards in the form of containers, the global scale of these networks, and the fossil fuels that power all of the machinery, including, of course, the ships. But trucking, shipping, any kind of transportation is still largely powered by fossil fuels. So, and then, of course, the newest of the technologies that we're going to talk about is telecommunications. And so, having these global networks of communications. So, we have electrons moving around, we have atoms moving globally, we have bits moving globally, we have information moving globally. I'm not going to speak to it very much, but even things like the rise of civil aviation and the sort of personal mobility and transportation of humans moving globally in a way that they didn't or they did to a much, much smaller degree a century ago and certainly 2 centuries ago. So this is sort of the change in our world that's been shaped by fossil fuels, that's been shaped by that exponential growth, and that's been shaped by cooperation. So this is a quote from Amartya Sen, who's a Nobel Prize winning developmental economist. And he writes that we generally have excellent reasons for wanting wealth, he writes. So this is not because income and wealth are desirable for their own sake, but because typically they're admirable general purpose means for having more freedom to lead the kind of lives that we have reason to value. The usefulness of wealth lies in the things that it allows us to do, the substantive freedoms it helps us achieve. So the argument here is that money, if we think about the difference between the global north and developing countries, we often sort of focus on money and wealth. And Sen makes the point that the reason to have money is not for money for its own sake, but because of the freedom, because of the agency that it then provides to you. And I submit that our infrastructural systems, so this includes water, sewage, electricity, transportation, communications. I live in the Northeast, so natural gas is a big one, as well as supply chains. These are a collective provision of this kind of general purpose means for living these kind of lives that we have reason to value. And so on a day-to-day basis, most of my sort of ability to choose what I want to do on a daily basis doesn't derive from my income per se. It actually derives from the fact that we have these shared collective systems, that our collective wealth has gone into making these network systems. And this became, of course, very clear for people who were working at home, particularly people who were working at home during the pandemic, that if you have, electricity and you have heating and you have potable water coming to your house and sewage being taken away, and you have access to telecommunications, most of your basic survival needs were met by collective systems, these shared systems. And that's actually one of the reasons why secure housing is really important, because it, among other things, it's the nexus to these infrastructure systems, which are the way that we collectively meet our needs. So there are many examples of agency, but one that I just want to highlight is what I think of as, in a way, the purest example of agency is artificial light that makes it possible to see at night. And this is actually a satellite view from NASA of India. And this first image was taken in 2012, and the second one was taken in 2016. And in fact, artificial light has been a remarkably reliable proxy for development, that in general, when people get access to more income or more wealth, one of the things that they more or less immediately use it on is artificial light, because artificial light literally gives people more time in their day, more functional time to work. So this is the city, I think it's the city of Plattsburgh in upstate New York. And I actually have family here, so I actually spent time here as a child. It's just over it's like 20 miles, 30 miles from the Canadian border. It's outside Montreal. And the reason why I'm talking about Flashback today is because I want to highlight this, which is about 5 years ago, a number of Bitcoin mining concerns went to Plattsburgh and set up sort of mining operations there. And the reason why they went to Plattsburgh, which, as it says, is for cheap energy, Plattsburgh had a long-term electricity contract that provided them with relatively inexpensive, actually quite inexpensive electricity, which is part of the appeal for Bitcoin miners to be there. But there was a town quota for the total amount of energy that the town could consume. And the Bitcoin miners came and they used up so much energy that the town as a whole hit its quota. And that meant that everybody in the town got bumped to a higher electricity tariff. And because the electricity in this town was relatively inexpensive, many people were using electricity to heat their homes, which meant that in the winter of 2017, their heating bills spiked. So essentially now we're in the realm of their basic survival needs spiking. And I'm raising this because this actually sort of highlights this issue of power providing agency or energy providing agency, that in general, we treat this as sort of unrestricted power, that the point is that as an individual, then once you have the power, you can make your own decisions about how to use this. But this can run into limits if there's a limited amount of electricity or a limited amount of energy available. So the reason why Plattsburgh has inexpensive energy is because their energy comes from here. So this is the Niagara River downstream of Niagara Falls. In the foreground is the New York Power Authority's hydroelectric power station in Niagara Falls. And in the background is its counterpart in Ontario across the river in Canada, which is the Ontario Power Generating, the Sir Adam Beck station. So these two hydroelectric plants were built out and produce inexpensive hydroelectricity. And Plattsburgh, which is relatively close, has a long-term contract to produce this, to get inexpensive hydro. And this is actually true of a number of places. It's true of Quebec. If you grew up in many places in Canada, because hydro is so prevalent, it's really common to call your electricity bill your hydro bill. But this is also true for many places in the Western US. So that was why Plattsburgh's electricity is so cheap and why Bitcoin miners went there, because it's coming from this renewable source of hydroelectricity, just as I said, downstream of Niagara Falls. So I'm going to zoom out. This is literally the million-mile view. This is an image of Earth taken from Lagrange point 5, which is about 1 million miles away. This sort of blue marble view. And what we can see at the scale is that the Earth is awash in solar radiation, right? And if you run the numbers, you can show that the amount of energy that is incident on the Earth as solar energy. Let me back up and do the other way. If you look at North Americans and you look at their energy usage every year, the footprint every year, and then you said, well, what if every human on the planet used energy at the same rate? That would still only be a fraction of a percent of the incident solar energy on the planet. So when we talk about energy as being renewable, this is what we mean. That renewable energy, there's incident energy on the planet, it is coming in every moment of every day, and it is coming in abundance in order to meet human needs. The challenge that we're, of course, working on is figuring out how to harness that effectively. But renewable energy is abundant. The other characteristic of aluminum energy is the one that I've already alluded to with hydroelectricity, which is that the incremental cost of renewable energy is effectively nil or close to nil. Because the raw energy coming in, the source of it, is free, it's in the environment, you need to pay the operating costs and you need to pay the capital costs to build things out, but the incremental cost is nil. So if you were running a power station off fossil fuels, for every kilowatt hour of electricity, every joule of electricity that you use, you need to pay for the fuel that goes in. That is, of course, not the case for renewables. It's not the case for things like hydroelectricity. You still need to pay, in both cases, for both renewables and fossil fuels, you still need to pay operating costs and distribution costs and capital costs, but it changes the economics of it drastically to not have to pay the sort of incremental cost. And this is, of course, well known, particularly in the world of computation. So this is the first Google data center in the Dallas, Oregon. You can see the water behind it, and the reason why it was located there was for the same reason why Bitcoin miners went to Plattsburgh, because of the access to the inexpensive hydroelectricity that was possible, and hydroelectricity in quantity that was possible. And my understanding is that Google is actually building out this data center still further, so they're making it larger. So if we're focusing on computation and digital technologies, renewable energy is abundant, and renewable energy, so there's enough essentially for everyone. Renewable energy is also extremely inexpensive, and that makes the economic case for switching computation over to renewables extremely clear. So essentially, it's a way of drastically reducing your operating costs, because switching to renewables usually means that it's possible to have lower operating costs in energy. And so you can see this being reflected. So Amazon became the world's largest corporate producer of renewable energy. Microsoft will be carbon negative. You see in the text it says that they plan to shift to 100% supply renewable energy. This is Netflix's net zero. Netflix, interestingly, because their streaming actually comes from Amazon's data centers, Netflix is actually only a small portion of this. It's actually their sort of streaming and computational costs. Most of what Netflix is looking at is their cost of actually creating their productions. But there is a sort of this well-grounded sort of economic argument for moving to renewable energy if in the sort of computational digital world. The other thing that I want to highlight is Moore's law's lesser known cousin, Kumi's law, which is that computation has actually become significantly more, exponentially more efficient over time. And so Kumi's law phrases it as the number of computations per joule of energy dissipated doubles about every 1.6 years. And you can put this the other way around, which is that for a given computation or a fixed computing load, the energy or the battery size or the electricity needed to power that about every year and a half is going to be cut in half. So putting this all together, renewable energy is abundant, renewable energy is relatively inexpensive because of its very nature from an economic point of view, and also computation is becoming more efficient over time. All of this is great. The thing I have not talked about, you'll notice, is the other aspect of course, when people talk about renewables, they rarely talk about it as, oh, like this is it is abundant and inexpensive and we should do it. And we tend to focus on the other side of it, which is that we have excellent reasons to stop doing it. And this is a refinery. And the thing I actually want to highlight here is that our infrastructural systems serve two purposes, or really it's the same purpose on both sides. So one is that we can use energy and networks to bring resources to the beneficiaries of those networks, to the users, to the consumers of those networks. But anything that can allow you to move stuff efficiently around the earth can also be used to displace or to diffuse the consequences or the harms of those. So the same networks that bring us, and I say us because as someone who lives in the global north, I am 100% a beneficiary of full stack infrastructure. All the same networks that bring goods, that bring power, that bring sort of all of these things to my home, to my body, wherever it is, are also used to displace those, often used to displace the impacts of those. And so in the case of, so sometimes that's diffusion. So in the case of greenhouse gases, that means that when fossil fuels are burned, the harms, the greenhouse gases are diffused to the atmosphere. So I said that, North America, I talked about the North American energy footprint. It's about 10 times higher than the lowest energy footprint using nations on the planet, which include places like Bangladesh. And Bangladesh is a low-lying nation. It's an energy poor nation compared to places like the US and Canada. And they will be, of course, just as impacted by CO2 in the atmosphere and have fewer resources to respond to it. So this kind of diffusion, and if you hear about microplastics in the ocean, that's also an example of this kind of diffusion. But in general, the history of infrastructural systems has been about taking, using the networks to sort of centralize the benefits and then to displace the harms onto other communities, onto other times, or to diffuse them. So I showed you a photo of the New York Power Authority looking on the riverside. This is actually the entrance to it. It's named after Robert Moses. Some of you may know the story that Robert Moses, the urban planner in New York City, the last thing he did before he retired was went to Niagara Falls and built, or actually rebuilt, the power station there to ensure that New York City would have sort of adequate power in the future. And as part of doing this, he went to the Supreme Court and asked the Supreme Court to break a treaty obligation with the Tuscarora peoples, which is a reservation that is immediately adjacent to this site. And the Supreme Court sided with him. The treaty obligation was broken, and half of that reservation is now underwater. It's actually, as I said, the reservoir for this site. But that pattern of using these networks to centralize the benefits and displace the harms, of course, is really common. This is another sort of similar example, and we sort of see this everywhere. This is, some of you may recognize this. This is the former Bankside power station in London, now the Tate Modern. So it's a museum in the city, and the power sources have been moved outside of the city. And we see this is true for all sorts of systems. But it is especially true, so I was mostly talking about energy at the outset, but with fossil fuels, and in general, this is also true for matter. So it's not just where does the energy come from, but that energy involves actual atoms, right? Actual materials, whether it's pulling oil out of the ground or whether it's shipping goods around the world. There's another piece of these networks, which is the material piece. So I want to spend a little bit of time talking about that. So energy is the currency of the material world, right? So energy is the thing that we use to move things around, but there are still these atoms that are involved. And this is actually a photograph of glass being made, which is an extremely glamorous usage of energy in the production of the material. But all physical objects that are fabricated require energy to extract the raw materials, to fabricate them, to transport them. So all physical objects embody a certain amount of energy, but they also, of course, involve atoms, right? They're made of actual matter. So I'm going to ask the question, which is, what happens if we fully decarbonize and we transition to renewable energy? And it turns out that there's actually a historical precedent, not a great historical precedent, unfortunately, but I want to spend a little bit of time talking about that historical precedent of what happened in a previous time in history when this happened. So this is an aluminum ornament, I guess, for lack of a better word, consisting of a number of putti. It was made by Christofle for Napoleon III in the middle of the 19th century, and it is in fact made from aluminum. So in the mid 1800s, aluminum was a precious metal. It was considered to be like silver, this light, silvery, beautiful, lustrous substance. And the reason why it was a precious metal is not because aluminum is rare. Aluminum is not rare. Aluminum is, I believe, the third most abundant element in the Earth's crust. The reason why aluminum is a semi-precious metal is because very little of it appears in that metallic form. Aluminum binds so tightly to oxygen that almost all of it in the Earth's crust appears as aluminum ore. Very little of it appears as metal. And so in order for it to be sort of even known as a metal, it needed to be extracted from its ore. And that was a tedious and expensive and time-consuming process. It was really hard to make aluminum. And it meant that when you did get that silvery, lustrous material, you made fancy things like gifts for the emperor out of it. This, of course, is not how we think about aluminum today. And what actually changed was, first of all, the invention of a process to refine aluminum. And so that process is known as the Hall-Héroult process. It was created in the mid 19th, or sorry, in the late 19th century by two people, actually, one in the US, Hall, and one in France, Héroult. And they figured out a way to refine aluminum by essentially dissolving aluminum ore in molten salt, which is glowing hot salt, and then running electricity through it. And then the aluminum would be refined out from that. And that process is actually still used today at scale to make aluminum. And this is an aluminum smelter. And I have to say, the first time I saw a photo of the Google data center, my first thought was like, wow, that looks like an aluminum smelter. And the reason why it looks like an aluminum smelter is because both of them require vast amounts of electricity. And both of them also use water for cooling purposes. So they're typically located, as I said, like long flat buildings that are located, in the case of aluminum smelters, at the nexus of transportation links rather than sort of fat data links. And they almost always have water picturesquely in the background because they have sort of very similar needs. So because the refinement of aluminum is such an electricity intensive process, the thing that made it possible to sort of happen at scale was cheap hydroelectricity by and large. Not exclusively, but that was certainly a big driver in it. And that was certainly a driver in the US and other places. And so that meant that we essentially went from the sort of decorative gift for emperors, semi-precious metal, to what we're familiar with, right? Aluminum is literally disposable now. So in this case, access to cheap renewable energy really supercharged this whole process. It went from taking something that was precious, and it went from basically supercharging this whole extraction, disposal, and waste process. And so this is actually a depleted bauxite mine in Hungary, I believe. Bauxite, which is aluminum ore, is typically strip mined. So everything I said at the beginning about fossil fuels, energy, putting that energy in, using that to do things at bigger and bigger scales, can also be used with atoms and be used to sort of extract and waste and discard things. So where does this leave us? Well, going back out to the million-mile view, we are awash in solar radiation, but our planet is also at the bottom of a gravity well, right? It has a finite amount of matter. Not very little goes up and down that gravity well. There's very specific atoms that can do very specific things. This is where my background as a material scientist is important. But also that those atoms are sort of distributed around the globe in particular configurations and in particular places. So the actual matter on our planet is what's actually finite, and how we use it then. And now we're starting to run up with the limit if we hear about things like microplastics in the oceans, or of course, CO2 in the atmosphere. We're starting to run up the limits, both in terms of understanding the environmental effects of the extraction, and we're starting to sort of have a much better understanding of the effects of putting these atoms in, like as waste, into our shared atmosphere. So thinking now, coming back to the idea of computational and digital technology, we spoke about the energy side before, but there's of course also the physical side of computing, right? The material side. And as I think probably most of us are familiar, the number of sort of electronic devices has also vastly increased. Even just focusing on smartphones, which are now of course numbered in the billions. And one of the things I just want to highlight here, and this is just looking at the minerals in a smartphone. You can see these various things. You can see aluminum, titanium, lithium is one we hear a lot about, tin, the silicon, the potassium in the glass screen. So all of these actual sort of specific atoms that are used to manufacture electronic devices. So all of these have to be extracted from somewhere, they have to be fabricated, and then they're typically discarded somewhere. And again, many of you are probably familiar with the sort of e-waste repositories. This is the one outside Accra in Ghana, where electronic waste is discarded. So sort of coming back to this, I suppose, so where this actually all leaves us is that what we have done, essentially, the way we sort of think about materials in general is the way that the thing that we've done with aluminum, right? It's like we're just going to extract and then consume and then discard. And I'm sure, again, you know, the idea of right to repair or planned obsolescence are concepts that are familiar to many of you. But we can ask ourselves the question, well, what happens if we decarbonize and we transition to renewable energy? So when people say, oh, it's not economical to recycle this, or it's not economical to extract the raw materials from this, often, not always, but often what that means is that it's too energy intensive, right? It costs too much money because it would require too much energy to do. And in fact, aluminum and glass and steel are all fairly well recycled because it actually takes less energy to recycle it than it does to do the incredibly energy intensive process of refining all of those in the first place. So it's economically effective to recycle, which really just means it's energy effective to recycle. This is 100% not true for plastic. Right? Like if you burn plastic, you get energy, which means that if you want to go from in the other direction, it's always going to take energy. If you want to tear plastic apart and reform it into new plastics, it's always going to take energy. And we see this in the sort of dismally low rates of recycling around plastic. But if you have access to abundant, clean, and inexpensive renewable energy, what does that change? And what it can potentially change is that it makes it possible to close these loops on these material flows. Excuse me. So I'm actually going to talk very briefly about two different companies that are working in this space. And this is not sort of an endorsement of these two companies. It's really, and everything is in relatively early stages, but it's really just a way of sort of examining the possibilities. So this first one is called 12. And 12 is has using a catalyst, which is this here that's been developed. In fact, one of the people who developed it is Tasha Cave, who was in the first graduating class of Olin College. She was a student of mine. And what 12.co does is that they are using this catalyst to pull carbon dioxide out of the atmosphere and turn it back into biofuels or feedstock or plastics using this sort of catalytic process. So this is, by its nature, an energy-intensive process. But if you power it using renewable energy, the fact that it takes a huge amount of energy to do it is no longer sort of an economic or a physical limiting factor. It becomes possible to actually run this process in reverse as an energy-intensive process rather than one that puts energy out, because just like hydro made aluminum feasible, renewables, other renewables can make this feasible. And this was the same logic. For example, desalinating water is a fundamentally energy-intensive process. Once you've mixed salt into water, it takes energy to separate them again. There's no way of getting around that physical sort of phenomenon. But if you have energy from clean sources like renewables, suddenly you change not just the physics of it, but or rather you do not change the physics of it, but you change the economics of it because you change where the energy is coming from, how much it costs, and what the impact that energy has on the environment. So closer to our topic at hand, this is a company called Ascend Elements that's actually located close to where I am in Westborough, Massachusetts. And they're involved in taking discarded lithium batteries from electric vehicles and pulling out the raw materials. So they're actually doing this, closing the material loops, taking discarded batteries, processing them, removing the lithium and other materials, and then upcycling them into new batteries, which in fact work better than the original batteries did. And so they're being funded by the federal government, along with other startups who are actually in this business of closing these material loops, of using energy and using new technologies to figure out, instead of focusing on extraction, to focus on closing the loops around materials. So where does this leave us? So despite, as I said, being ephemeral, being sort of flickering on our screen, the digital world has its feet firmly in the real world of energy and materials. And we are starting to enter this world of like, okay, we live in a world where energy is unlimited, but matter is still finite. And I actually kind of want to stress this for a second, because we're really, really used to thinking about energy as being a limiting factor, that energy is scarce and expensive, but we're really used to treating sort of physical objects as sort of disposable, right? They can just come from anywhere and they can go anywhere, and we use materials, essentially freely, without thinking about them as limited or scarce or anything of the like. But the reality is actually, from the million-mile perspective, the reality is exactly the opposite, right? That energy is unlimited, but matter is what's finite on our planet, and we are starting to run up against those boundaries. And so this is an incredible potential, right, for how we think about digital technologies and computation and the type of access people have and the type of devices we use. But it's a thing that we are going to need to sort of face consciously, to make this sort of shift in our mindset consciously, is to think about the fact that we've created all these systems that have really thoughtlessly or maliciously, have been about extractive and about displacing the harms to other communities. But we actually now have the opportunity to start thinking about how to make them fully renewable, and how to think about making particularly material systems, closed loop systems, and thinking about mitigating the harms. But this is no longer, this is well within the realm of technological possibility now, but it really is sort of fundamentally rethinking about how we think about these systems. So I actually just want to end, I said this was bookended with Ursula's. So this is Ursula Franklin, who wrote The Real World of Technology, which is a series of lectures. And she wrote that central to any new order that can shape or direct technology and human destiny will be a renewed emphasis on the concept of justice. So as we sort of think about these new technologies and the new possibilities of renewable technology, thinking about what that means for shaping the world that we live in. I'm going to end there, and I think we do have some time for questions. Thank you so much for your attention.
Thank you. We do have a couple of questions, and so let me queue them up for you. The first one is from Victoria, and she asks, can you explain why recycled batteries are more efficient than the original version?
So I'm going to say no. I'm going to recognize the fact that I haven't actually specifically done the research, but I will say that often the act of purifying something the first time means that you've actually done all of the sort of hard work of actually purifying it, and then you can sort of purify it further. But I do not know the specifics of like this technology, but the general case is you've done the hard work of purifying it, and you can purify it further still, rather than actually going from sort of like not pure to quite pure. You get to go from quite pure to very pure. So that would be the general answer, but I'm not sure of the specifics. I'd have to do a little bit more research.
This is intriguing. We have another one from an anonymous attendee. It's a bit long, so let me read it to you. Energy flows are thermodynamic processes, which are scale dependent. Information flows are code-based, likely scale independent. Some of the problems you described might be caused by the difference between thermodynamic and code-based processes, different speeds, different scales. For example, smartphones have new versions almost every year. Information flows are flexible and scale independent, but the materials of smartphones do not change easily. To solve some of the problems, how do we reconcile the seeming difference between energy flows and information flows?
I actually think that's to some extent, that's actually what Toomey's law gets precisely at, right? That the energy associated with computation has also been dropping as a factor of 2 on a regular basis. I know that there certainly are intersections between thermodynamics and information, in terms of, because there is actually a linkage to entropy. And I'm 100% going to say, like, that is not my area of expertise. I understand there's a link. I'm not going to get to it. But I think germane to this is this idea of the link between the material usage and the computation isn't a fixed solid, and the energy required is not a constant link. That's what Toomey's law illustrates, right? There are many ways to do the same computation in ways that are extremely energy intensive or extremely energy efficient. And again, as I think many of you know, that computation, we do computation in silicon, but of course, similar computation happens in slime molds. Computation happens in our brains, right? There's lots of ways to do computation. So there isn't a fixed link between the information and the physical system behind it. And that means that there's a loose link to the sort of thermodynamics of physical systems. I hope that gets at the answer.
I think you're pointing at least one of the tensions of it. I'm going to ask you a question. This is, I'm thinking of my wife, who she works for Qualcomm and government services. And she spent a lot of time worrying about the political aspects of getting the materials necessary to build phones. And of course, there's also political aspects of energy. I mean, we know them all around. So I'm curious, what do you see are the differences in the geopolitics of material versus energy? Do you see differences, or some easier to solve than
Yeah. So I think the fundamental difference is that renewable energy can be extremely decentralized and distributed. So fossil fuels are localized, they're atoms, right? They're localized to particular places on the planet. And that means that the geopolitics to having access to them goes through those places on the planet. The nature, the challenge, the challenge of renewables and the one of the advantages of renewables is that they are decentralized and distributed, right? So the good news is that they are everywhere, right? You don't have to go through sort of geopolitical bottlenecks to get access to them. The bad news is that they're extremely diffuse compared to fossil fuels, which means that you need to figure out the technologies to concentrate them and to harness them. And so that is fundamentally, I think, the difference between atoms and energy per se, and the difference between renewable energy and like that's the challenge between energy and materials, right? And that's why I actually think that energy is a much more, at this point, after 50 years of working on clean energy, and funding it and supporting that research and getting it out into the world, I think energy is a much more tractable problem than materials, because energy is kind of everywhere, and you can figure out how to use it, but materials really are in particular places on the planet, and you either need to figure out how to get them, and which means navigating and doing so in a way that is just and fair, navigating the geopolitics around them, or you need to figure out alternatives to them. And that's actually one of the things about why lithium batteries is kind of an interesting example, because on the one hand, extraction, reusing lithium basically means that you can limit the extraction and you can limit your kind of reliance on the geopolitics. On the other hand, if we're going to build out a renewable electricity grid, building it on lithium batteries is probably not the way we want to go, right? It's like, but also it's like a lost opportunity, because if we're looking at energy storage, there's no reason to take this technology that's extremely expensive and extremely portable, because it's grid scale energy storage. It doesn't have to go anywhere, and it doesn't have to be small, right? So using considering sort of alternate ways to achieve the same ends, but this is what will take the sort of concerted effort. And again, this concerted effort has certainly started, right? That to sort of figure out these alternatives, but energy and materials really are different. And we're accustomed to thinking about sustainability in a way that really entangles the two of them. And part of the reason why I wanted to speak to this topic was to actually disentangle them, to allow us to look at them both separately.
Thank you. We have a couple more questions. Kelly Bignoli says, Deb, since we're in a room full of library people instead of engineers for once, I'm wondering if you can speak to how us information workers can contribute to efforts around sustainable energy infrastructure.
The sustainable energy, so actually there's sort of two questions here, actually. So Callan, thank you for coming in. And I'm actually going to answer your question. I'm going to answer a slightly different question too. So, and actually I'm going to answer the other question first, which is in the short term, the thing on the material side, I think, is the thing that many information science and information technology people and librarians are deeply involved in, which is right to repair and understanding what you have, and sort of getting away from sort of planned obsolescence, right? And keeping things, because the longer you keep things out of the waste stream, right? That means that the slower the sort of supercharged cycle is going. And that means that the less extraction, the less waste is associated with that. And I know that's something that librarians and library science folks are deeply involved in, is helping people get the knowledge and the understanding to use their devices effectively and well. The other side is actually a little bit more challenging. How do we sort of move towards renewable energy infrastructure? So as an individual, there's a sort of a few pieces to this, right? So one piece is to sort of make the changes that you can make as an individual, but fundamentally, it's really about making these changes that are collective. One of the things that I think is a sort of a good place to start is to avoid being locked into non-renewable systems for the future. And so, for example, so we live in New England, and Boston doesn't have quite enough natural gas pipeline capacity, which means that during cold snaps in the winter, there's liquid natural gas tankers that come into Boston Harbor, and they shut down Boston Harbor and they bring in more natural gas. And it's incredibly inconvenient. And for a long time, the natural gas companies have been trying to build out more pipelines, and they haven't succeeded. People have rightly resisted. And this is a good example of sort of benefits versus harms, that the argument for the resistance is to not have the pipelines or the pumping stations in their neighborhoods. But the bigger argument for not building new pipelines is that we do not want to be reinvesting in these networks that make it easier and more efficient to do these things that we actually want to stop doing. And so one of the sort of individual level changes is that I can say is to support zoning rules about not building out. So there's municipalities that have new rules that mean that new builds can't have natural gas lines built in, right? That they need to be electrified, and resisting building out really infrastructure of the sort of all sorts. So whether it's municipal pipelines, as in Boston, or pipelines writ large, supporting not investing into the networks of non-renewable energy to try to start getting out of one kind of cycle of this is the network that works well, and into a different virtuous circle, which is how to get renewables to work well. So that, I would say, there's sort of an infinite number of starting points, but those are, but trying to think about it as, let's not get locked into fossil fuels, and let's actually start to build out systems in renewables. And Callan likely knows this, that Olin, we are in the process of getting approval to build out solar panels on our campus. So that's sort of a step to starting to move towards building out those networks that allow the same exponential growth and circle that led to the rise of fossil fuels. We can sort of put that into place for renewables, but it happens in all scales as individuals on up. Callan, sorry about that super long answer to your question.
It was a good answer. I have a question from someone who's expressing optimism, but somewhat guardedly, from Schulertown. So the question is, assuming extractive capitalists make use of the same cheap energy applied to lower energy extraction, is there a risk that the companies making use of cheap energy for more energy intensive recycling will fail in the market before we can make meaningful transition? Who's going to win the race?
Hi, Scholar. Yes, right? Like, that's part of the reason why this is the thing that thinking about it as a mindset is that if you use just the economics as the logic for moving forward, it's never going to be enough, right? And the way I sort of described this in the past is that sustainability, to capitalism, sustainability always looks like underutilization, right? Because the whole point is, if you're leaving something for the future, it's underutilizing it in the present. And so absolutely, right? There's sort of many ways in which this will fail if we think of it strictly in economic terms. And we don't, right? Like, the reason why there are like tax credits for electric vehicles is as a way of actually linking together the sort of larger public good policy issues with individual economic decisions. And so starting to do that at all sorts of length scales. And so the types of things that are on the table for this is, for example, the US government as the buyer of first resort for electricity, or for renewable electricity, right? So starting to make, and this to some extent is an answer to Callan's question, is that a lot of the sort of individual decisions are starting to make policy decisions at all length scales. And that's from the sort of household on to the nation state or international levels that are explicitly about decoupling these larger issues with the economic issues, so that we're not sort of fully reliant on let's only do things that are economically viable.
We have a question from Katie Shilton. Thanks for this fantastic talk. Do you have an idea for our students headed to work in tech companies about how to advocate within their workplaces for renewable energy? Are there things workers can do, or is this something we should be working on more at the political legislative level?
That is an excellent question, and I feel like I'm not necessarily the right person to answer it. I mean, I think this is, I mean, I wouldn't be talking about it if I didn't think it was a thing that all of us can be involved in as sort of citizens. I think that not just citizens, but as sort of residents and as people who sort of live in and benefit from these systems, and that would be true for tech workers. I think the one sort of I feel like the general all-purpose answer to that, though, is that to the extent that people in tech companies can work collectively is the way to sort of have power in the companies rather than trying to enact change as individuals. So I think that would be finding ways to unionize or to otherwise work collectively would certainly be the first step that I would think about in terms of making these sort of larger changes, just as it's true outside companies, right? For us to work collectively rather than as individuals to make these larger changes.
Thank you. Amanda French has a question, but I feel it's directed to many people in the audience, not just you. Do you think that information schools and CS schools are moving more towards recognizing and teaching materiality of computing than they have previously, or is this still not acknowledged?
Can folks answer that in the chat?
Yeah, why don't you?
I wonder if people.
I mean, I can tell you this topic, only briefly have I ever seen discussion in the America iSchool Dean's Group. So, Amanda says, yes, please enter things in the chat. I'd like to hear more.
I would also be interested in the answer.
Yeah. Victoria Van Heining has a question. I think you briefly touched on nuclear energy, but can you say more on how or whether you think it has a place in the future of our energy needs, either fusion or fission?
Yeah, so the power station that I actually showed you came online shortly before I did. It's just about 50 years old. And it's, I think nuclear is a really challenging and interesting example. And so I said early in the talk that I said that infrastructure systems and these technological complexity allow us to displace the harms or the potential harms to different communities, to allow us to diffuse them into the world at large. And nuclear is a really good example of making it possible for us to shift the potential harms into the future. And because nuclear waste has such a long half-time, so I mean, nuclear is technically not renewable because the fuel actually gets consumed. But I think the real challenge with renewables is feeling confident in a system that means that the harms that are being shifted to the future are going to be appropriately mitigated and dealt with. And so, for example, I know Finland, for example, is building a repository for nuclear materials called Incremental, and their big thing is like, okay, you know, in 10,000 years, if this material is still radioactive, how do we know that the people who live here are going to be still be protected from it? How do we mitigate the harms for something that's so far in the future? And I think that's the piece that with nuclear broadly, this idea of if you think about like how do we limit or mitigate harms, there's a real challenge. How do we not displace those harms onto other people? That includes not displacing harms onto the future. And I think it is doable to mitigate those harms. I think it is absolutely, that's the specific challenge that needs to be faced. And the real larger policy challenge is that we're sort of faced with the sort of near term of what's happening with anthropogenic climate change. And then we're like, okay, well, we don't have to worry about these things that are going to happen far in the future. In the short term, though, the two things I'm going to say are, in the short term, it takes time to build our nuclear. And so it's not necessarily the right path forward for things that are not already in play. And of course, there are many countries in which nuclear is already in play. Nuclear fusion, on the other hand, is a good sort of pointer to the fact that we don't have to have all the answers right now. So nuclear fusion, of course, it's not quite at the point where it's commercially successful not commercially, but like energetically viable. But it is a real pointer to the fact that we are in the process of actually developing the new technologies that are going to be renewable. So it's not like, oh, we have this set of technologies and we must choose this set of technologies. We actually also get to invest in developing, figuring out new possibilities. And geothermal is a good example of that, which is a thing that, you know, we haven't really heard that much about. But but this idea of like, okay, how do we move forward with this set of principles of building out new systems that mitigate harms or eliminate harms and don't just displace them? And then what does that look like for different kinds of energy systems?
We have one last question, which is always asked of authors. Does your book have a publication date yet?
Next summer, I hope. I actually just gave it to my editor. I just gave her a revised draft. And my sort of standard line about it is like, it's like planting a tree. It's a book that I wish I had written 20 years ago, but the next best time to write it is today, or I guess next year for it to come out. But I'm hoping for next summer.
Very good. Let's all thank Debbie Chachra again for this wonderful presentation, and thank you all for joining us. This is a fascinating talk. I certainly, unusual for us, I learned so much. Thank you.
Thank you so much. Thank you for the invite. Thanks everyone for coming.